Today, this is the heart of that course. We're going to talk about the free body diagram. And if you can draw the free body diagram, most of the problem from now on is going to be easily solvable. So what we're going to do, I'm going to train you today on how to draw a good free body diagram. Then we'll go from there. But before we do this, we have to do a little bit of a revision. I'm going to say that, or talk about Newton's laws again. Newton's first law that says everything will stay at rest, or it will move with a constant speed as viewed from the inertial reference frame unless there is an external force acting on it. Second law, it says that all the forces acting on the object, if you add them as vectors, they will cause the object to move with an acceleration. So all the forces will equal to the mass of the object times the acceleration. Third law, it says that forces always occur in action-reaction, always occur in pairs. There's action, there's always a reaction that's equal in magnitude and opposite in direction. And a little bit of comparison between mass and weight. Mass that's a scalar quantity. Weight, that's a force. Weight equal to the mass times g. So mass is a scalar quantity. Weight is a vector quantity, and it has a magnitude and direction. So there is a difference between mass and force. So the mass of that student, that's 55 kilograms, but her weight is, if we assume that acceleration due to gravity is 10 for simplicity, then her weight is 550 Newton. Now, look at this. An astronaut that's Nagy in a few years, an astronaut, actually he will kick that heavy stainless steel ball on the ground, on Earth. It's really heavy, it's a bowling ball. And he will hit it also on the moon. So if he hits it on Earth or he hits it on moon, which one will hurt more, on the Earth or on the moon? Or I will read it again. A year later, the same astronaut kicks the bowling ball on the moon in the same manner with the same force. His foot will hurt on the moon more than Earth, less than Earth, the same. Okay, the same. Some people, we have few people saying the same. Does anyone have other opinion? Farida? It's less? 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 But not more. Yes, of course. There's a difference in the gravity. That I agree. Of course, there's a difference in gravity. The gravity on the moon is less than the gravity on Earth. So if I kick it on Earth, what will be the force acting on my foot? So if I kick it with the force F, what will be the force acting on my foot? The same force F. Okay? The same force F. That's Newton's third law. Now I'm going to go to the moon, if Nagy allows me to go with him, he's the astronaut. Then I'll kick the same ball again. Right? With the same force F. So will it hurt more? Will it hurt less? Or will it hurt the same? So people are saying less and people are saying the same. So who said less? Farida said less. Why do you think it's less?
Because when the gravity on the moon is less than the gravity on Earth, that means that you're going to need less force because it's both.
No, I'm going to kick it with the same force.
But you're not, because the volume, you don't
The weight of the ball on the moon
Mass is the same, but weight is different. I agree. Mass is the same, weight is different. Why am I feeling hurt? Why will I feel hurt?
Because the force of the ball acting on you is different.
In what direction?
Again,
So if I push it in that direction, the force on my foot and my foot is going to be along that direction. Does that have to do anything with gravity? And along that, yes, F equal ma along the x direction. That direction, not that direction. And so we have to separate between, because force is a vector quantity. So if we're talking about force equal ma, then you have to specify along which direction. Right.
acceleration is like this.
The gravity is like this. So if I'm going to carry it up, it will have, I will put less force to carry it up because the weight is less on the moon. But if I'm going to kick it that way with a force F, it's going to kick me back with the same force F. So if I do that on Earth, or I do it on the moon, it's going to be the same. I'm going to feel exactly the same hurt. Yes.
Why when we kick a electric ball, it doesn't hurt?
When you do what?
When we kick
A light ball? It does kick you back with the same force exactly, but with much less force, because now you push it with the less force. If you push it with the same force,
why does this move and then
okay. Because now we're talking about another physical quantity, which is momentum and energy. So if you can keep that question again and ask me that again when we talk about chapter 9, then this will be a good time to address that. So write it down, please, and highlight it. And when I go to chapter 9, ask me the same question again. There's another phenomena that will come in, that's momentum. And then we have to talk about conservation of momentum and what kind of collision happens now between my foot and the other object. If it's an elastic or inelastic collision, we have to talk about this. We're not there yet. Okay? Good question. Very good one. Okay. Okay, guys, should we move on? Okay. So it's gonna exactly feel the same. I'm gonna skip that. Free body diagram. Now, for any object, if we need to study the kinetics of any object, we have to concentrate on the forces acting on the object, not the forces from the object, only the forces acting on the object. So if I want to study the kinetics of Mahmoud, right? And I'm going to push Mahmoud in that direction, or I'm going to put some force on him, I should concentrate only on the forces acting on Mahmoud. Because if I push Mahmoud, he will push me back with the same force. So I should not concentrate on the forces from Mahmoud. I should focus only on the forces on Mahmoud. This is a common mistake we all make. Sometimes we get confused and we mix the forces together. We should focus only on the forces on the object. Only the forces on the object. Now, that's why I say the key phrase here is for an object. We need to focus on the forces on that object. So if this is an object, a ladder, that's tilted on the wall and on the floor, I need to consider all the forces on the ladder and from the ladder. We need to consider all the forces on the ladder and from the ladder on that diagram. So I actually have drawn those forces as you see them, but I made only one mistake. I made only one mistake. Vanessa or Nagy will find out that mistake for us in 1 minute. And if any one of you get the mistake first, he gets 1% bonus. Nagy? Now, Vanessa and Nagy. You have guys 1 minute to find that mistake, and if you get it in 1 minute, you get 1% bonus. Now, you can start.
The force acting from the plank on the earth.
From the plank on the earth. Force acting from the plank on the... That's the gravitational force. That one? This is the force acting, this is the force from earth on the plank, that's the gravitational force from the earth on the plank. This is correct actually. This is not wrong, this is correct. Nagy? The FPF, that one, this is the force from the floor on the plank, and it's going to be along some direction. So I put this is the direction. So actually this is also correct force. What else? Vanessa? That one. This is the force from the plank on the floor. So the force on the from the plank on the floor, the plank will be pushing the floor down, and it's going to be along some direction, which is also, this is correct. There's nothing wrong with it. Vanessa, no, now Nagy. Okay, thank you, Nagy. Actually, there's no mistake. Okay, Sharif. What are the forces acting on the plank? No. I said now, guys, I have drawn all the forces from and on the plank, and I claimed that I made a mistake, and I wanted you to find out the mistake. Actually, there was no mistake. So actually, there is no mistake. This is all the forces. We have 3 pairs of forces acting on and from the plank. There is a gravitational force that's attracting the plank down. This is mg, the famous mg. And of course, there is the opposite and equal force for that. That's the force acting from the plank on the earth. The plank is also attracting earth in its direction. Since there is touching here, there is an action-reaction force between the plank and the floor. And we have also, the plank is touching the wall, there's an action-reaction force from the plank on the wall and from the wall on the plank. So those are the 3 pair of forces that we have. Now, if we need to consider only, Nagy, if we need to consider only the forces on the plank, on the plank, so only on the plank, that's why I put that round shape in here. So if all forces on the plank, those are only the forces on the plank. The force from the wall on the plank, the force from the earth on the plank, the force from the floor on the plank. Those are the 3 forces acting on the plank. This, we call that the free body diagram. So if we draw all the forces acting on the object, we call that the free body diagram. Now if you tell me if which one? on the plank. So on that object, what will be the gravitational force on that object? It's always pointing down. Even if you tilt it that way, it's always pointing down. So that, we call that the free body diagram. Since that object is at rest, it's not moving. If the plank is standing on the pole and the floor, that means that plank is at rest. That means that if you add all those forces as vectors, and guys, when I say as vectors, that means that you have to consider the direction in that case. You have to be careful when you add them as vectors. You end up you end up having 0, because there is no motion, there is no acceleration. So some of the forces in that case will equal to the mass times the acceleration, but the acceleration is 0 since there is no motion. Then that means that some of the forces, if you add them as vectors, will give us 0. Farida.
So if, let's say you add
That's exactly what I should do.
So you put it like this and then one would go down and then it would automatically go back to 0?
Say that again.
You got the 3 vectors.
Yes.
You put them so that the arrows are touching the arrows are touching
Yeah.
the vectors.
Yeah.
They're going to all end up, they're going to go back to origin?
Yeah, if Farid is saying, now if you draw those 3 forces, are they going to look like this? Yes. Yes. They should. Yes. That's a very good observation. So, because if you add them that way, you get 0. Okay. Graphically, Farida was asking me if to add them graphically. We'll know how to add them. So if you could just give me a minute, we'll take another example. That was just an example to show you how can we draw the free body diagram, and to show you that since there is no motion, then the net force should equal to 0. Then that means that if you add those 3 vectors, 3 forces as vectors, you get 0. A very simple one. I'll start with a very simple problem in here. We have an object that has a mass m. That mass is 2 kilograms. 2 kilograms. We push it with a force along the x-axis equals to 10 newtons. What is the acceleration? What are we supposed to do? Before we do this, some of you will say, but that's a very simple, easy, that's a very easy free body diagram. Do we really have to do it? Yes. Yes. Because if you get used to use the free body diagram in the simple problems, you will use them in hard one, and it will make your life much, much easier when you use them in the hard problems. So I'm going to start with drawing the free body diagram. Mai or Mariam, would you volunteer to tell me how can I draw this free body diagram? That's the object. Farida. So what else? So what else? What should we do? We should draw all the forces acting on that object. So that's the force Fx. Do you have other forces acting on the object? Yes. Gravity, thank you. It's acting from the center of the object down. That's mg. Do we have other forces acting on the object? Vanessa saying, well, since it's touching the floor, then the floor must be pushing that object upward. The action. And most of the time we're going to call it the normal force. And the normal force. The force will acting on the object perpendicular to the surface. That's why we call it the normal force. And so now those are the 3 forces acting on the object. So we have done step number 1. Step number 2. What to do? We write down Newton's second law, which states that sum of the forces will equal to mass times acceleration. Someone will say, since this is a vector, then you have to break this equation into 2 equations. Sum of the forces along the x-axis would equal to mass times acceleration along the x-axis, and sum of the forces along the y-axis would equal to mass times acceleration along the y-axis. Let's translate. That's step number 2. Step number 3, let's translate that from equation, from just Newton's second law, into our problem. What are the forces along the x-axis? Fx. Vanessa is saying that's Fx. That's only Fx. That should equal to mass times acceleration. Look at that equation. What's Fx? What is the numerical value for Fx? 10. What is the numerical value for the mass? 2. Can you calculate the acceleration? 5. It's going to be 5 meters per second square. So from that, we can find that AX would equal to 5 meters per second square. Now we have solved the problem. But I will actually go a little bit further and talk about that force as well, though it's not needed. No one asked us to get it, but to actually show you how useful is that. Now, what are the forces along the y-axis? N and mg. Let's add them. Let's add them. I is saying, well, N has to be positive because it's along the positive y-axis, and mg has to be negative because it's along the negative y-axis. That should equal to 0. Why 0? Because there is no motion along the y-axis. The object is only moving along the x-axis, and there is no motion along the y-axis. So that's why the acceleration along the y-axis is 0. So that whole quantity will be 0. Then from that equation we can find out that the normal force that we did not know any information about before should equal to mg. Is it always mg? No. Is it always mg? The answer is no, and we'll find more examples that actually will have n not equal to mg. Yes.
If the force was not the parallel axis, not implied from
Okay. It's in here. Okay, guys, do you understand that problem now? Okay, good. And that's the solution. I have drawn all the pair of forces that we have on the object. Then I have concentrated only on the forces that's acting on the object, Yasmin. Then this is my free body diagram. I have specified my coordinate system. This is very important since we are dealing with vectors. Then I have applied Newton's second law along the x-axis and along the y-axis, and we got all the information that we need. That's the acceleration, AX, that's 5 meters per second square, and the force from the floor on the object equal to mg, which is, I called it here the normal force. I have called it here the normal force. Before I answer, you take your case, which is it's coming. Do not worry about it. Let's look at that another example in here. We have an object that us, someone of us, is standing in the elevator, and that elevator is moving up with an acceleration a. Now, my question is, let's look at that normal force between the floor of the elevator and the object. The normal force from the floor on the object. Is it going to be more than mg? Will it equal to mg, or will it be less than mg? Before we go to answers, I would like to be systematic. So I'm going to follow the 3 steps again. Okay? So what I'm going to do is, I'm going to do the free body diagram, write down Newton's second law, apply it, translate it in the step 3 from symbols to numbers, then we'll find the solution. Free body diagram. Yasmin, that's the object. Since we're talking about the object, then I should draw only the object. What are the forces acting on the object? And it's acting from here, but I will draw to here only. Yes, and mg. Perfect. There's no forces along the x-axis. There's no forces along the x-axis. So those are the forces acting on the object. Oh no, I don't want the answer now. I know that most of you guys can give me the answer right away, But I have to explain that with the same systematic way that I used before, so you can actually get to use it. Yes, for sure. Force between? From where? No. No. There's a force on the elevator. The wire that's pulling the elevator up. There's a force from that wire on the elevator. That's the tension. We'll talk about it later. But I'm talking only about the object inside the elevator. And this is all the forces acting on that. So I apply it in second law. Sum of the forces along the y-axis, since we're talking only along the y-axis, will equal to mass times the acceleration along the y-axis. What are the forces? That's very important to get the minus and the negative direction of those forces. It's going to be N minus mg equals to ma. It's not zero. If you are driving your car and your car is moving with an acceleration in that direction, you inside your car are moving with the same acceleration as viewed by someone standing outside, of course. And that's the case here. So that should equal to m times the acceleration. Is it positive or negative acceleration? Was it positive? It's positive because it's along the direction of the positive y-axis. Okay, now N will equal to mg plus ma. Look at m. Look at N now. Is that more than mg? Is that less than mg? It's more than mg. That's why, guys, when you get in the elevator and if the elevator is going up with an acceleration, you feel that you are a little bit heavy. Actually, you can try it more. If you're carrying a bag in the elevator, and if when the elevator starts to go up, not with the constant velocity, at the moment that change direction, change its status from at rest to moving, then we have an acceleration. You will feel that as if the bag are a little bit heavier. And if you're going down, if the elevator is going down, this is negative, right? And this is going to be negative. The bags will feel, you will feel as if the bags are a little bit lighter. Okay? So, yes. And because this is my coordinate system. Now, I look at that force. Is it along the positive y? Then it's positive. If it's along the negative y, then it's negative. Okay? So now we know the answer. For that part, it's going to be N will be more than mg. N will be more than mg. Tension. Someone was talking about, asking me about the rope that we hang that elevator from. That's tension. If we pull something, if we pull a rope, a wire, then there will be force acting on that wire. Any piece of the wire, if you choose a small part in here and look at the mass in here, there will be a force acting on it, and that force we call it tension. So if you cut that wire into two halves, there will be a force. Assume this. If I'm pulling the wire and Mahmoud is pulling the other part of the wire, then Mr. Haney comes in and he cuts that wire. What happens? I fall that way and Mahmoud falls that way. It's exactly because there will be a tension pushing that part in that direction. That's why I fall that way. And there will be a force. That's the same force, tension. Forces happens in pairs. Push that part in that direction. That's why Mahmoud falls in the other direction. So we have a force here. Excuse me?
The tension force, right? The force of activity.
That's tension. We call it tension. But it's a force. Yeah, it's a tension force. Okay? I'm pulling and Mahmoud is pulling, and we both are giving forces on each other. So if we're not moving, if I pull and he pulls, then if we're not moving, if we are not moving, that means that the force I put in Mahmoud equals to the force Mahmoud puts on me. That's Newton's third law. So if Vanessa, so if you choose a small part of the rope in here, this is part, and if you look at the forces acting on it, I'm pulling it that direction with the force F, and Mahmoud is pulling it with that direction with the force F. That's why the rope is not moving, and that part is not moving, and the net force acting on it is 0. So if we cut it, then there will be a force pushing in that direction, and there will be a force pushing in that direction. That's why we both fall down. So that's another action-reaction kind of force, and we call that the tension. I'm going to skip that. And this is what I explained to now. If you choose a small part, only a small part of the rope or of the wire, and look at the forces acting on it, there will be a force to the right. That's T1. I'm pulling, and Mahmoud is also pulling in his direction. So if you look at that part of the wire, there will be a force along that direction. That's T1. That's from me, and force along that direction. That's T2. That's from Mahmoud. If you add the forces, if you apply Newton's second law, you will say that T2, because that's positive x, T2 and T1 will equal to mass times acceleration. If the rope is not moving, if the wire is not moving, that means that the acceleration is 0, then T1 will equal to T2. That's why we said that tension will be equal in that case. That's those two tension. But if it's moving, then we have to find out then the two tension by default. If Mahmoud is actually pushing me in his direction, is pulling me in his direction, and we both are moving, then the wire is moving along that direction, there is net force. The force of Mahmoud that Mahmoud is pulling me with is going to be more than the force I pull him with. That's why there will be a net force, and if there is a net force, there is an acceleration. Okay, guys? Okay. No, there is no tension inside the mass of. If you hang it, yeah, we'll see. Yes, of course.
I don't see a difference between force and tension.
It's force. Tension is a force. You're right.
Then why can't you say F1 and F2?
Why did I say T1 and T2 you mean? Right? I assumed that T2 is going to be different than T1. And if that happens, we will have an acceleration. But if they are equal, that means that the acceleration is 0. So that's what I said. If Mahmoud and I are pulling each other, and if there is no motion, then T2, that's the force that Mahmoud pulled me with, T2, will equal to T1, the force that I'm pulling Mahmoud with. That's if there is no motion. Okay, but if there is motion along that direction, Mahmoud direction, then T2 will be more than T1. And if there is force along my direction, then T1 will be more than T2. Okay, but if there is no motion, this is the more important part, then T1 will equal to T2, will equal to T. Yes?
In the other slide, when you say F max is equal to T2 minus T1, that means the absolute value of T1 is
No. No. T2 is positive? Yeah. I added them as vectors. Okay. Now, if you have a rope, if you hang a mass with the wire from the ceiling, that's the case of that projector. We hang it from the ceiling with some rod, with a rod. I'll assume for now that the rod is massless. It does not have a mass. What is the tension of that rod? What is the tension on that rod? How did we do? How did you get that, Mahmoud? How did you find that the tension would equal to mg? Mahmoud said right away it's going to be equal to mg. Mahmoud. So Mahmoud said, why? I will follow your way. I will draw the free body diagram. So he draws the object M. Then
There are mg
since that elevator is not falling down, sorry, that projector is not falling down and it's not flying up, it's not moving. That means that T, which is positive, sum of the forces will equal to mass times the acceleration. This is that part, T minus mg will equal to 0. 0 because there is no motion. That means that T equals to mg, and that's what Mahmoud gave me right away. Okay, guys? Now, can you solve that part? Let me show you. Now we have a fish. It's being yanked upward out of the water using a fishing line that breaks when the tension reaches 180 newtons. So we know that that wire, if the tension on it equals to 180 newtons, it will break. The string snaps when the acceleration of the fish is observed to be 12.2 meters per second squared. What is the mass of the fish? So we know that that string is going to be broken when the acceleration is equal to 12.2 meters per second. That means that the net force on it, at least it's going to be 180 newton. At least, or more. It can be more than that. So, but at least it's gonna be 180 newtons. Now, can we find the mass of that fish? Of course, this is a very real life problem. So let's actually be systematic again. And I'm sorry you're going to be hearing the free body diagram so many times from now on. And so do not get bored from it, because it's very useful, and especially when it comes to exam time. So guys, Kordi, let's draw the free body diagram together. This is the fish that has a mass m, which we don't know. Now let's draw the free body diagram on the fish. That's the acceleration. This is the acceleration. That whole thing moves upward. That whole thing moves with an acceleration equal to 12.2 meters per second squared. That's the acceleration. The fishing line. There is a tension on the fishing line. That's the force acting up. And we have one more force. Farida is keeping doing this. She's telling me that actually she's not doing this. She's doing this. That means that there is a force down. That's mg. And Mahmoud has been saying mg. There is a force on all of us. It's a gravitational force acting on any object on Earth. Kordi? That's mg. Those are all the forces acting on that object. Now, that's your free body diagram. Step 2. Sum of the forces equals to mass times the acceleration. What are the forces acting on that object? Of course, to be more accurate, since we're talking only about the forces acting along the y-axis. So T, which is positive, T minus mg will equal to the mass times the acceleration. Times the acceleration. The fish is moving up with an acceleration 12.2 meter per second. That's why that acceleration is positive. It's not negative. If it's moving down, it would have been negative. Now, P minus mg equals P equals to mg plus ma. Look at that equation. We have only one unknown. I forgot your name. She now is saying you don't have the mass, you don't have T. Do we? Yeah. She knows right. She knows saying that T, since that fishing line is going to be cut, that T has to be either 180 or more. So the minimum value for T is going to be 180. Now, can you calculate M? 8.2. We'll see. That's 8.2. Good. Okay, guys? More examples. Okay. More tools. Pulleys. Pigs and pulleys. This small cylinder that you put a wire on it, and it's just all what it does is transfer the direction of the force. It transfers the direction of the force. So if I pull in that direction with the force F down, there will be a force F along that line as well. Same force F. So that we call that pulley. If it's that assumption that it's only transfer the direction of the applied force, that assumption happens only if the pulley is smooth, does not have any friction, and if it's very light. If we can ignore its mass compared to the other masses, we hang it from it, and if it's frictionless, if it does not have any friction. And that's what we're going to do. I'm going to assume that it does not have friction, and I'm going to assume that it's very light. For now, when we go to chapter 12, we're going to change that. But for now, it's massless and frictionless. And all what it does is to change the direction of the force. Look at this. This is an example of a mass. We hang it from a wire. That wire goes over a pulley, and we attach it here to the wall. My question here is to find the forces. What is the forces on the wall from the string, from the wire? What is the force on the wall from the wire? On the wall, this is the forces on the wall from the wire, from the string. Okay. If you look at that object, the tension, since there is no motion, the tension will equal to mg. So the tension is mg. All what does all what the pulley does is it changes that direction to that direction. That tension, instead of having the tension up, the tension is going to be along that direction. Mg.
Here in this part,
Mhm.
tension is down, and in this part, the tension is
Let's draw it. Sorry. Free body diagram. This is the object M. That's mg down, and the tension is up. The tension is pulling this object up. You hang that object by the wire. That means that the tension is up. Okay? So this is the direction of the tension. Now you have a pull in here. So the tension is up, and at that point, since there is no motion for any element of the wire, that means that the net force on it should be 0. So if the tension at that point is that direction, the tension along here is going to be along the opposite direction. Newton's third law. So because it's not moving. And even if it's moving, it's going to be along the same direction also, but the magnitude of the tension is going to be different. The magnitude of the tensions is going to be different. We'll see. So do not rush into this. So if this is T, this is T. This is the wall. Now, what is the forces acting on the wall? That's the same tension T. The force, if you acting on the wall, that's T. And we found that T equals to mg. That's why you find me writing here, the force on the wall from the string equals to mg. Springs. Now, what am I doing? We talked about wires, tension in wires. We talked about pulleys. And we're talking about the last tool that we're going to have, that's springs. A spring is just a wire that we make, a spring outfit. That's a spring. The spring, if you leave it unstretched, does anyone have an elastic band, guys, boys? Elastic band? Oh, thank you. An elastic band will do as well. I don't want a spring, I want an elastic band. Yeah. Do you need it? Okay. This is a spring. This is a spring. This is what we call it a spring. Sorry, that's too small. Okay, that's a spring. That's a spring, guys. And you can push on it so it gets shorter, or you can extend it and it gets longer. That's a spring. So actually, that's a spring. That's a spring. If I pull it, if there's no papers, till it gets longer. If I push it, then it gets short. We call that spring. So that's what we're going to study now, that spring. Elastic band, you know, that small elastic band that we put around our money. Sometimes when you go to the bank and you get your money with in elastic band, that's another form of a spring. So if you have a spring, it will have unstretched length. It will have a length. The length of that spring is, I'm going to call it x, and this is its unstretched length. That x, if you apply force on it, it gets longer. And so if you have a spring, and if you pull it with a force F, the force F is going to be directly proportional to the extension of that spring. You put more force, the difference in the length, its length is going to be more. More force, more delta X. Okay? So we can remove this by putting a constant K. So the force will equal to some constant K times delta X. Guys, what is the units of K? Units of K, Newton per meter. And if you look at the units for K and you try to understand what is K, K is, if you put 1 Newton, force of 1 Newton on that force, it will extend by how much? This is the meaning of K. So, your car suspension system, it has a spring, right? Did anyone look at the car suspension system? It's a huge spring. It's very heavy, huge spring. It's similar to this, but it's each round it's like 20 or 30 centimeter in diameter, and the wire itself is very thick wire, very thick piece of metal. So that's a spring, and if you try to push on it, it's really hard because it has to suspend the car. It has to stand the weight of. So if we compare that spring with the spring of your car suspension system, which one has more K?
Okay.
Yeah.
The one of the car,
Why is the one of the car?
it needs more force to.
So Nada is saying the one of the car, it needs more force to push it 1 centimeter, but while that one, it needs a little force to push it 1 centimeter. So obviously the one of the car has more K than that small one. Okay, so the force acting on the spring will equal to K times X or times delta X. And if you look at the equation on the the equation on the screen, you'll find a negative sign. That negative sign has a meaning. It means that if you are pulling that spring, that force actually, it's not the force that you're pulling the spring with. It's the force, the spring trying to pull itself back to its original position. We call it the restoring force on the spring. The force, if you pull this in that direction, what's going to happen? The spring will try to pull back along that direction. And we call that force the restoring force. And this is actually what you see. This is the restoring force. Okay? So if I push in that direction, if you extend the spring, what will be the direction of the restoring force? To the right or to the left? My right or my left? You pull it that way. That's the spring. This is the spring. So I'm going to do this. So this is going to be the direction of the restoring force. What is the direction of the displacement? My hand move the displacement. What is the direction of the displacement? To the right. So the force is always in the opposite direction to the displacement. I'll say it again. So the force is always in the opposite direction to the displacement. That's why we get that negative sign. Mai or Mari? Mai. I'll do it again. Now there is a spring. Okay? And if I pull it in that direction. So look at the displacement of my hand. If I pull it in that direction. What is the direction of the displacement? My hand displacement.
Yeah, I get that because when you said right, it was your right with my left, so I thought it was.
Okay? Okay, I'm going to pull it in that direction. So what is the direction of the displacement? To the right, right? What is the direction of the restoring force? To the left. That's why you get that negative sign. So the negative sign means that the restoring force and the displacement are always opposite in direction. That's why we get that negative sign. But the most important part is the restoring force is directly proportional to the displacement with the constant, and that constant has a name, that's the force constant. We call it the force constant. And it has a unit of Newton per meter, and the more the force constant of the spring, the harder for you to push it. Okay guys? So that's another tool that we're going to use in this course, that's the spring. And we use the spring actually in scales. You have seen before scales that use a spring. Now, we have two cases. Case number one, we have a mass M, Nagy. This is very important. This is going to be in the exam. We have a mass M attached to a string. That string runs over a pulley. Then it's attached to a scale, spring system scale. So it has a spring inside, somewhere in the spring inside. And then it's attached to the wall. The other system is a mass M it's attached to a string. The string runs over a pulley that's attached to a scale, and the scale is attached from the other side by another string that runs over a pulley to another mass M. Those two scales will have a reading. The scale here reads the weight of that object. The scale reads the weight of that object, and its reading is 4 pounds. 4 pounds. What will be the reading of that scale? 0, 4, and 8. Okay. The scale in that case reads 4 pounds. And we need to find out what will be the reading of the scale in case number 2 when you have two masses attached to it. And I have put 4 answers. And if you look at most of the time when we put an answer, each one of them carry a misconception except one. That's the correct one. That's why sometimes the numbers make sense. 0, 4, and 8, all of them make sense. 2 of them carries misconception, and the third one is the correct one.
I have a question.
Sure.
The mass, the
Scale.
scale, does it consider the 2 forces or just
Can I rephrase your question in here? Sharif is saying, what does the scale do? What does the scale read? The scale reads the tension. The scale reads the tension in the rope. That's what does the scale do. So now I think I have solved the problem. 0, 0. This is tension 0. This is nothing pulling it. But this has some tension. Do you think it's 0? Bishoy, do you think it's still 0? In the 2 cases, do you think in that case it's going to be 0?
But does it measure the tension? Does it measure the mass?
It measures it measures the tension. Yeah. It measures the tension. Yes.
It measures the tension.
Yes.
So if it measures, if the tension is in the opposite direction of will it be negative, the tension? Is this like this?
Yeah, well, we have agreed when we talked about the tension that the tension is a force, and we know that force always occur in pairs. So if I was pulling Mahmoud, that's the example I gave you in the first of the class. If I'm pulling Mahmoud in that direction with a rope, and Mahmoud is pulling me in the opposite direction, the tension on the wire, there is a tension. That's why I said if Mr. Hani comes in and he cuts that rope, we're going to fall in that direction. The tension is going to push Mahmoud along that direction, and the tension is going to push Mahmoud along that direction, me along that direction. So if you take a small piece on the wire and you calculate the net force on it, not the tension. If you calculate the net force on it, there will be a tension T in here and a tension T in here. So the net force on it is going to be 0. Net force, but the tension is not 0. Excuse me? Oh, but again, the scale does not read the net force. The scale reads the tension. How many of you have a bathroom scale? All of us, right? All of us. We have a bathroom scale. And when you stand on that scale, what does the scale read? It's the mass, not the weight, because you get kilograms. But what does it really read? The normal force. It reads the normal force from the scale on you. And of course the normal force is the mg. Yeah, of course, but it does really read the normal force. That's why if you put that scale, Yasmin, if you put that scale in the elevator, when you go up and you go down, the reading is going to be different. Did your mass change? Did your weight change during going up and down? No, it didn't. It reads, but the normal force doesn't change by the direction of the motion of the elevator. That's what we have shown to you a minute ago. Normal force and we're equal to mg plus ma or minus ma depending on the direction of A. So the scale, the bathroom scale, reads, it really reads the normal force. That scale reads the tension. Now, we should focus on the tension. Draw the free body diagram. Be systematic. If we draw the free body diagram for this, what will be the tension? What will be the here? What will be the tension here? mg. Right? So what will be the tension here? mg. Now, here, if we draw the free body diagram, what will be the tension? mg. So the rope, that rope has a tension of mg. No. Now you're getting the net force. You're not measuring the tension. When you say, yeah, of course, but it's not the net force. Concentrate on what I'm saying. I'm saying you're calculating the net force, not the tension. Okay? If one of the two masses is different than the other, there will be motion. But in that specific case, the tension in the wire is just mg. So the reading is going to be 4 pounds. That's similar to that one. Nothing is going to change. One more time. This is a very, very nice problem, by the way. One more time. The most important part is to realize that the scales, they either read the tension or the normal force. We should know that. So now, my goal is to find the tension in that wire. In that wire. Forget the other one. It's not important. As long as they are the two masses. What is the tension in that wire? In here. mg. If we draw the free body diagram, if I draw the free body diagram, that's the free body diagram, that's the mass m. Then you have a force mg pointing down. You have a tension T pointing up. Then the tension will equal to tension minus mg equals to 0. Then since there is no motion, that means that the tension will equal to mg. That's the tension in that case. So the tension is mg. And if you draw the other free body diagram, the other mass, same mg, same T. So that wire will have a tension T along that direction and a tension T along that direction. So if you choose any element in here, it will not move because the net force on it is 0. Net force on it is 0. But the tension in the wire is T. Farida, if I'm pulling you with a wire, and you're pulling me with the same wire, and there is no motion. So I'm pulling you with exactly the same force, and you're pushing me with exactly the same force. Okay? And along the wire, at Amira's location, we're going to color Amira. That's the wire. It has a red part in there. That red part, if we look at the net force on it, it's 0, because we have a T in that direction and T in the opposite direction, so the net force is 0. But what will be the tension along the wire? Tension along the wire. It's T. It doesn't matter. They are the same. They are not two. This is the same tension. Yeah, it's exactly as in that case, in that specific case. This tension here is the same tension here because one second. Okay, because they have the two masses. But if you change the masses, the tension here is going to be different than the tension here, and you will have motion. What will that depends on the acceleration between them. That depends on the acceleration.